So the question was about the twin paradox and how it's actually tested. The easiest way to test it is to notice that we get cosmic rays at the surface of the Earth. Most of the cosmic rays that reach the surface of the Earth that cause clicks in Geiger counters are muons. A muon is a fundamental particle that's made when you explode a nucleus and the parts are allowed to decay. And if you create muons in the lab, sitting still in the lab, we can do this, it's easy to do. They live about 1/1,000,000th of a second. But muons that are created at the top of the atmosphere, when very high energy cosmic rays hit the top bit of air and blow up nuclei and create these showers that reach the Earth, live much longer. They live 20 or 30 or 50 microseconds in order to reach the Earth. Even at the speed of light from the top of the atmosphere, it takes longer than 1/1,000,000th of a second to reach the ground. So what's up with that? How can this possibly be? Well, the answer is they're moving very fast. They're moving close to the speed of light, and therefore their clocks slow down. So what looks like a microsecond, 1/1,000,000th of a second to them, well, their clock is going slow, and it might take 25 or 50 microseconds for us to see that because we see their clock barely moving due to relativistic time dilation. So that's a test that that's a check that we actually have juniors do in the junior physics lab, is measure the lifetimes of muons that are standing still, measure the lifetimes of muons that are coming from the top of the atmosphere, measure this number. Offhand, I don't know the number, but it's big. I think it's like 25. And that's an example of time dilation happening. Yes, it is weird. It's unexpected. You're not used to it. But that's because you live at a small speed. You mostly live standing still. As far as the velocity of light is concerned, you don't move at all. And the universe is different. We just see a very simplified view of the universe. Could we get the first slide up, please? So today's topic is astrophysics, sort of widely construed. And this, to me, this sums it up. This is an old Calvin and Hobbes. It says, look at all the stars in the universe, just goes on forever and forever. It kind of makes you wonder why man considers himself such a big screaming deal. And of course, Calvin comes back with, that's why we stay inside with our appliances. The chapter in the book actually takes a slightly different approach to this, but I'm going to cover a very similar group of topics. What I want to stress today are three things. The universe is a big place, it's an unexpected place, and we're figuring out how it works. So all three of those will be themes that come up today. And if you're a future president someday, a little bit of scientific humility might help you. So we'll start with astrophysics here. What's that? Oops, where'd it go? Why don't we just keep the slides up there? Nobody needs to see me, and I'm not going to be drawing anything on the board for a little while. So for a while, let's keep the slides up. What's that? It's a picture of the Earth. Where was it taken from? Somewhere out in space. The Earth is a big place, right? I don't know anybody who's walked all the way around it. You think Berkeley's a big place? Well, Berkeley's just one of 9 or 10 UCs in one state, in one country, on one continent. The Earth itself is a really big place. But actually, on an astronomical scale, not so much. Here, for example, is the Earth and the Moon. When you look in the night sky, it's actually been brought much closer. The Moon is actually much farther away than that in a real picture, but here it is sort of by scale with the size of the Earth. The Moon's a pretty big place, too. Many of you have seen a picture like this as we scale out. Those are and I claim there are 9 planets in that picture, and I'm not going to debate whether Pluto is a planet or not. I don't think it matters. This is Earth. Can we dim the lights quite a bit, please? This is Earth. This is moving outward from the sun. The sun would be down here. There's a little gap, and then Mars, and then a little gap, and then Jupiter, onward to Saturn, etc. And out here is Pluto. One of the reasons there's a debate about whether Pluto is a planet or not is notice that this tendency out here is toward really big hunks of gas, and then there's this little tiny bitty thing out there. It doesn't look like it fits. If we move inward from the Earth, there's Venus and there's Mercury very small. Now, the misleading thing about pictures like that, or pictures like this, is it gives you the impression that, the solar system is like, maybe factor 10 bigger than the Earth. If we really pushed on it, we'd discover that we could maybe put 50 Earths across this guy, but it's imaginable in size. But if your scale is the Earth, anybody ever walked from here to New York? Anybody walked from here to Sacramento? Right? If your physical length scale is hundreds or maybe thousands of miles, this picture is very misleading to you. This is 12,000 miles across there. This is what the solar system really looks like. First off, you can't ignore the biggest thing in the solar system, which is the sun. And even burps, even when the sun just, gets a little bit of indigestion and throws out a big chunk of gas, this is an actual picture of the sun. This is hydrogen gas that was burst out of a pair of, it's called a solar prominence, and it was just thrown out of the sun. That's huge compared to all these. Here's Earth again, right there. But then when you look at how much empty space there is, there's a lot. The sun in that picture is to scale. You see the sun? There's the sun. And these are all of the orbits going out here. It's hard to see this one. This is Jupiter. But coming in from the middle, this is Mercury, Venus, Earth, Mars, Jupiter. Saturn doesn't fit on the screen. If we want to go toward the outer planets, we can get that. There we have, now all of this inner stuff is this is the orbit of the Earth, this little tiny circle that's embedded in here. Here's Jupiter, the one that we considered very far away. It takes Jupiter 12 years to go around its orbit. Its year, the length of time it takes to go around the sun is 12 times ours. By the time we get out here, this is Neptune, the last circular one, and this is Pluto. Again, another reason that Pluto is a little bit unusual is it doesn't have an almost circular orbit. It's a big empty place. The solar system is a big empty place. Now, it's not entirely empty. It's full of lots of little rocks and dust and things that will, when they get close to the sun, will start to emit gas and be called comets, asteroids, all sorts of interesting things fill there. And we could easily talk for a week about the interesting little stuff. But I want to continue on to pass a little bit further out. This is called the family portrait. It was taken by Voyager 1, a spacecraft that flew for many years to get to the place where it is. It was 40 AU, 40 astronomical units from the sun when it took this picture. And AU is the radius of the Earth's orbit. So this spacecraft was 40 times the distance from the sun that you are now, 40 times roughly 90 million miles, or roughly 6 light hours away from the sun when these pictures were taken. This was so far away that the radio signals that it used to send back these pictures took 6 hours to get here. Now, just to give you a scale, it takes a couple of thousandths of a second for radio signals, a few thousandths of a second for radio signals to get to New York. It takes just a couple seconds to get to the moon. It takes 9 minutes to get to the sun. This was 6 hours. So what you're actually looking at is the sun was sort of here in this picture, and it had a little camera that could be pointed at a spot in the sky and take pictures. These are blow-ups of the individual planets. So here's sort of the inner solar system with Earth and Venus. Mercury was too close to the sun and couldn't be photographed. Jupiter was here. Most of this glow, some of this glow is due to defects in the camera. That line is due to a defect in the camera. But most of it is just the dust and junk in the solar system. All the way out to here, this is Neptune. Pluto wasn't visible for this picture. It shows you there's not a whole lot of anything in the solar system. The planets don't make up a lot of density in the solar system. It also shows you a relatively amazing thing. This is a spacecraft that has left our solar system in one sense. It's farther out than anything we would call a planet. So, do you know what today is? Does anybody know what today is? Cinco de Mayo. Okay, Cinco de Mayo means something, but it's also another thing. What happened in the United States on the 5th of May? I'll give you a hint, 48 years ago. So 48 years ago, Alan Shepard became the first American in space today. That's not a long time on an absolute scale. It's less than 50 years. It's within living memory. Many people, I remember it. Many people remember it. And in the time since then, we have managed to get something all the way outside our solar system to take pictures like this. Incidentally, you know what yesterday was? Yesterday was Star Wars Day. And if you don't know why, ask the person who's sitting next to you later on. Okay, so this is a blow-up of those pictures of the individual planets. These are the individual tiles. Those huge Saturn and Jupiter actually were resolved. They look like dots, but you know, disks. But Earth was just a dot. This band here is due to a defect in the camera. It was picking up some glare. But there's the Earth. You can't even see the moon. It's a big place. As you go further and further out, you discover that that's actually not the end of the solar system. The ancients knew about, well, they knew about Earth, of course, and they figured out the moon pretty quickly. And they very rapidly noticed that Venus and Mars, Jupiter and Saturn, behaved differently from the stars in the sky. They'd be in different places relative to the stars as time went by. They call them planets or wanderers. With modern telescopes, we've found more planets. We've found moons around planets. And it turns out that outside of this area that we think of as the downtown solar system is something called the Kuiper belt. It's pronounced several different ways. It's spelled K-U-I-P-E-R. All the dots out here are observed objects, chunks of stuff that are well outside what we used to think of as the solar system, but are gravitationally attracted to the sun. They're part of our party. Here's our inner there's Jupiter and Saturn. Here we get out to the outer gas giants. And then this thing is a belt of other objects that we found that essentially surround the sun. They're all orbiting. They're not falling inward. That's good. They're going around. They've been around there for a long time. One of the arguments about Pluto is whether it's just the first of these that we discovered or not. Maybe it is, maybe it isn't. That's for other people to decide. Beyond that, we're starting to run out of observations. But, you know, again, one of the themes is we're figuring this out. And as time goes by, telescopes get better. The computers that analyze the data let us look at more pictures from telescopes. Looking at pictures actually takes a significant amount of time. Telescopes can take pictures faster than people can look at them. So teaching computers to look at them and find things is very important. We're still getting observational data on this, but outside of that Kuiper belt, outside of the solar system that we know and love, it seems to be another rather complicated cloud. It's a cloud that's a big sort of fluffy cloud with a disk across the center of it. Way in the center here, that big, is our entire solar system. The solar system you were taught about in the 3rd grade all the way out to Pluto is right there. This is just a cloud that surrounds it of things that eventually become comets. They're the things that some passing star perturbs them a little bit, and they get bounced out into here, and they eventually fall into where the sun is, and they become comets. It's the Oort cloud with 2 O's, O-O-R-T. You don't have to remember that, but you do have to remember the idea that we're slowly figuring out that our neighborhood in the universe is actually a rather complicated place. Something that the ancients thought of was, well, there's the sun, and there's 4 planets on the Earth. Oh, don't forget the moon. End of show. It is actually a very complicated place with a lot of detail. As we explore this neighborhood, we're starting to find more and more interesting things. Again, look here. Here's solar system, all the way out to Pluto, that outer ring there. Blow that whole thing up a little bit, zoom out so that that's Pluto. This is the orbit of a body called Sedna, S-E-D-N-A. It's the farthest out known body. The orbit it takes such a very long time to go around that there's no way that we'll see that orbit, but we can predict it from where we found the thing and how fast it's moving. It's pretty far out, and even it is just the very inner part of this cloud that contains all the comets. So we're still exploring these things telescopically. We're learning more about the neighborhood. That's one branch of astronomy or astrophysics. But to a physicist like me, it's simultaneously not satisfying from a fundamental physics point of view. Our neighborhood is just made up of piles of stuff, and we probably understand the rules by which it was made. We just want to know why it's like that. So it doesn't really illuminate the history of the universe to me. And at the same time, it doesn't really awe me all that much. It's just data. The thing that you really notice when you look at the sky is stars. Lots and lots of stars. Now, this is an astronomer's convention that we have up here, where they use white with black dots on it to represent stars. It's just easier to print things that way back when we printed stuff. So what you're looking at is a constellation, Cygnus the Swan. Yeah, that's supposed to be a swan. And all these big dots are bright stars, and all these little dots are less bright stars. When you look in the sky on a night where there's no clouds, how many stars do you see? Like 100, maybe? 35? Well, there's like a dozen in Orion, and everybody knows how to recognize Orion. So maybe 300. I grew up in New York City. Until I was halfway through my first year of high school, I lived in New York City. It has a lot of junk in the air, particularly when I was growing up. It's actually less bad now. And it has a lot of light going up from the city and bouncing off that junk. So the sky is not very dark. The sky is not black. It's sort of gray. And a lot of dim stars would be lost in that gray. So my view of the sky was something like that. Yeah, maybe there are 50 or 100 bright stars, and then maybe there are like another 300 or so little tiny stars that I haven't bothered to learn the names of. But it actually looks something like that. If you ever get for those of you who haven't done it, go find a nice dark night, no moon, no clouds, and go sit on a mountaintop somewhere. You know, a real mountaintop, not Mount Tam, where the sky is really dark. That's the Milky Way. These are stars. These are stars. Not just too many stars to count, too many stars to see. There are a lot of stars in the world, in the universe. And when you look out at all those stars, it just seems inevitable to me that there's a question that occurs to you. What do you think the first question that occurs to anybody who looks at that many stars is? Well, some people say, are we alone? Are there people on those stars? Other people will look at that and will say, what's the quiz question for today? So, quiz time. So here's our quiz question. Number one, the Drake equation is about how long the universe will exist, how many civilizations are trying to talk to us, where the universe came from. And the second part is, do we know the answer to that equation? Do we know the number? use the traditional order, A, B, and C. And for this one, let's call that one A and this one B. Say again? That's all the questions there are. That's it. 2 questions. Okay. How long? You don't want to decide. You want to decide? Yeah, okay. Let's collect them, please. And now that they're moving across, I was just informed that your reading's not due until Thursday. This is what I get for being only a part-time lecturer. So I think what's going to happen is we're just going to count it as an attendance slip, even if you didn't happen to read this thing. So, yeah. Okay. And with that, let's go on and talk about the answer. That's Frank Drake. And about 45 years ago, he started thinking about whether we could do science with this question of are we alone. There are philosophical writings dating back almost 6,000 years on the question of whether there are other beings in the universe. Many of them didn't get the idea of stars and astronomy and stuff. The question of are we alone has been around for a really, really long time, but it's only within living memory that we've been able to actually start to do science. Part of science is building mathematical models, and Frank Drake, who's from Santa Cruz, came up with this equation. Now, it's not really a way of finding the answer. We don't know the answer. We know it's somewhere between 0 and infinity, but we haven't really narrowed it down more than that. It's a way of thinking about what you need to know more about. It says, well, really what we've got here is a possible number of civilizations, and then a possible number of civilizations becomes from how many stars there are and what fraction of those stars have planets and what fraction of those planets are habitable and what fraction of those planets have life on them and what fraction of the life grows up to be a civilization and what fraction of those civilizations are even doing anything technological that we might be able to detect and what fraction of those haven't destroyed themselves. This was the 60s, don't forget. Everybody was worried about destroying themselves. So we don't really know that. And you can start by speculating. You can guess. But it's easy to be wrong by factors of 1,000 on things like what fraction of planets have life on them. We don't have any data on that. But we've made a lot of progress in 3 different ways since then. We're getting very good at detecting planets. Originally, the way that the first planets were discovered, not ours, but ones around other stars, was by noticing that if you've got a big planet that's revolving around a star, there's a little bit of a reaction on the star. The star moves a little bit because this planet is slinging around it. Now, this effect is noticeable only if you've got a big planet like Jupiter. But if the planet is either big or close or both, it moves the star back and forth a little bit, and maybe you can see that. And it moves it front and back a little bit, and maybe you can see that, because when it's coming toward you, the light will be blue shifted by the Doppler effect. When it's going away from you, it'll be red shifted by the Doppler effect. And if you can detect blue, red, blue, red, blue, red, that's something that's got something orbiting around it. So this is one way to find them. Another way to find them is this way, which is called occlusion. A star is really a dot. Oops. Well, I don't know how to make that go. A star is really a dot. You can't see it. You can see our star, but you can't see others. But if a planet goes in front of it, it gets a little tiny bit dimmer, a tiny fraction, usually less than 1%. But if you have a very reliable measurement of the brightness of a star, and every year and a half it gets a little bit dimmer, that means a planet's going in front of it. And then finally, if your telescopes get good enough, you can actually start to image them directly. This is a made with an interferometer. That's actually a star, and these are a pair of planets. So eventually, we've gotten good enough at actually seeing them. We're starting to be able to see them, and within 5 years, we'll be able to see them well enough to know if they have water on them. The number of planets we are detecting is rising with time. Across the bottom here is year. Across the up and down is number of planets detected. So we're getting better at this. We're detecting 20 or 30 planets. And within a few years, if things go well, we'll be able to think about the first couple of terms in the Drake equation. We may even be able to tell in 10 or 15 or 20 years what fraction of those planets have our kind of life on them. Not just telling whether they've got water, but telling whether they've got oxygen in the air. Oxygen won't exist on a planet unless there's something that is free oxygen in the air won't exist on a planet unless there's something that's freeing it, because it will very rapidly combine with the rock and get pulled out of the air. You need life or something like it to put a free oxygen in an atmosphere. That's why Mars and Venus don't have very much free oxygen in their atmosphere. And even it's being proposed now that you look for light that is more left-handed versus right-handed, because the chiral molecules, the molecules like DNA, RNA, proteins, et cetera, in our kind of life have a twist. And light that reflects from green leaves is slightly twisted one way more than the other. And so by looking for that slight twist, maybe that would be a sign of life. We're getting smarter about some of these numbers. Some of the ones farther down, like how long civilizations live, that's going to be hard. So another approach is to try and find things in the universe. This is a picture of somebody by the name of Jocelyn Bell in the early 60s, and what's behind her is a large radio telescope. It's essentially a gigantic TV antenna pointed at the stars. The picture here is from a logbook. It's a discovery of an extremely regular signal from the sky, much more regular than the technology that we had at that point in the 60s could make. It was a better clock than any clock we could make. How do you know that? Well, it's actually sort of an indirect argument, but you know, a really excellent clock. And immediately, a couple of people proposed, well, that's a technological sign. That's a GPS signal or a digital TV signal or something like that from some remote star. What that turned out to be was a pulsar, a very rapidly rotating, very dense star, and every time it rotated by, it was like a lighthouse. It was beaming out a beam of radio waves, and every time it went by, it went pulse, pulse, and because it was very massive and very rapidly rotating, that was a very regular pulse. The Earth's 24-hour rotation period is extremely regular, too. So having something rotate regularly, that's not a big surprise. But for a little while, it was thought that that might be people. Even though that was eventually figured out, a whole bunch of people decided that they were going to look. And Ohio, or either Ohio or Ohio State, I don't remember, built something called the Big Ear. This is a football field. It was Ohio, not Ohio State. They got a new football field, so they took their old football field and converted it into a gigantic radio telescope. This is a little tiny building. Radio waves from the sky would hit here, be bounced back to there, be concentrated there. They could look for radio signals from the stars. And they found one. Here it is. Time goes this way. This is really old technology in the early 70s, I think. These are all different places where the signal could be, different frequencies. And then the line printer would print this line, and then this line, and then this line, and then this line. For a very brief interval, there was a huge, brightest signal that this had ever seen in a very narrow frequency. Nature makes things that are wide frequencies. Light is lots of colors. White light from the sun, you know, maybe there's a little more red in some stars and a little more blue in others, but it's many different colors. It's only things that are man-made, like lasers, that would make one color. Similarly, in radio waves, there are a lot of ways for the stars to generate lots of frequencies. And there are a lot of ways for noise to just sprinkle stuff at lots of frequencies. But finding something like that is thought to be, well, maybe that's a sign of technology. Unfortunately, this is the only occurrence they ever found. And science deals with reproducible things. If they went back the next day and looked at the same spot in the sky and got the same signal, that'd be different. Or if they looked back and found it slightly differently, that'd be different. But this never came back. And after 30 years of looking, that's still the best signal we've got. That caused a lot of enthusiasm and caused this telescope, which is called Arecibo. It's been in 2 James Bond movies. How big do you think that is? I'll give you a hint. Those are cars over there. This is the building where the people hang out. That's another building where people hang out. It's a valley in Puerto Rico, which they turned into a telescope. This is not a telescope that turns. You can't tilt it and look, let's take Puerto Rico and tilt it a little bit to this side so that we can look at that part of the sky. You wait for the part of the sky that comes over, and then this is the ear. This is where the radio waves come in from the sky and get bounced up into there. You can move that a little bit on these cables so that as the sky goes by, you can sort of track it for a little distance. You can watch a place in the sky for about a minute, and then you got to look at something else. So it's extremely sensitive because it's really big, but it can't look at anything with any attention span. It generates a huge amount of data. That's a very sensitive radio receiver. It receives lots of different frequencies. It's hard to find a signal in those, much like the problem with telescopes making too many pictures. So the people at SETI at home actually wrote a program that you can run on. This is now several years old, and I'm sure all of you have heard of it. To analyze all this data, they convinced people like you to run a program on your computers when your computers aren't doing anything that will sift through this data. This is frequency this way, higher frequencies, lower frequencies. This is time this way. Here's a second of data, second of data, second of data, looking for something. It's actually hard to find because another star might be moving around. Our planet is rotating. Their planet is probably rotating. All of this is going to mess with the frequencies. It's really hard to find this, and a huge amount of computer time has gone into it, finding exactly nothing. This is a picture of the Allen telescope. I can't remember what Allen's first name is. It might be John. He's one of the co-founders of Microsoft, has a pile of money, and is building a whole bunch of these, which are basic. Here's a building to give you some idea of the scale, which are telescopes that will look at the sky for the purpose of gathering yet more SETI data. We're looking really, really hard. Someday we might find something. The other approach is to try and talk to them. Anybody know what that is? That's a telegram. Carl Sagan, on 3 weeks' notice, managed to get this, which is about that big, put on a Pioneer spacecraft, which was, at the time, was thought to be was going to be the first spacecraft to leave the solar system. You're sending this thing off. It's going to spend the next millions of years traveling around the galaxy. You'd like to write your name on it. It raises an interesting question of how do you write your name on it? How do you describe, well, you individually, not such a big deal. How do you describe humanity? This is a hydrogen atom so that they can get some scale. This is sort of our picture of our solar system, and there's the path of the spacecraft. That's what the spacecraft actually looked like. This is two people, and to give whoever finds it some scale, that's the spacecraft. So they say, oh yeah, the spacecraft's like this big, so these people must be like that big. And hopefully they would figure out that something about people. There's this wonderful little debate at the time it was made was, so is his arm stuck like that? What, if you've never seen people before, it's not clear what you would get from this. 4 years later, they got another opportunity, and they sent this. Now, you got to remember, this is 1977. This is a phonograph record. It's gold-plated, and it's got a track on it, and they put a little needle in it, and there are instructions on the back. On the grooves are on the other side. Here's this same thing, but the people who found the other one aren't finding this one. The idea is you make a little thing that follows it around in the groove to make sound so you can hear it. It's I forget how many hours of people's voices and people singing and weird music, and I have no idea what the people who find this are going to think. This is a map of the galaxy which hopefully people will be able to use to figure out where our planet is from. And these things are going to take literally millions of years to get anywhere. This was sent from Arecibo. It's a radio signal. Ignore the color. The color is just there to guide your eye. It's a series of ones and zeros, which if you put out in the right raster form, it's a long series of ones and zeros. If you notice that it's the product of two prime numbers, and you say, oh, that must be a rectangle, and you fill in a rectangle with it, you either get something that looks like nothing, or you get this. What do you think? Can you figure out even with the color, can you figure out what it says? Well, that's probably the telescope, maybe. And since we know about people, that's people. I have no idea what the hell this stuff is. These are binary numbers up here. So we know how to count in binary. These are the binary numbers for atoms. And these are the amino acids. And this is DNA. I think if you knew about DNA and you were desperate to decode this, you might be okay. This is a person. It's somehow DNA. These are the planets. Sun, Mercury, Venus. Earth is special. We're standing on it, etc. I got nothing. I got nothing. And the amazing thing about this is it's going to take 25,000 years to get where it's going. They sent it to a very rich cluster of old stars that takes 25,000 years to get there. Why does it take 25,000 years to get there? Well, the distance between stars is big. The nearest star is about 3 or 4 years away by light, depending a little bit on how you count. Our galaxy, you all know about galaxies, our galaxy is about 100,000 light years across, roughly, and looks like this. This is not a real picture. This is one of the very first things I've shown you. It might be the very first thing I've shown you that's not a real picture. It's an artist's conception, because we can't get way up here, and unlike the Earth, we can't get way up here and take this picture. But we live in one of these arms in an undistinguished neighborhood of a somewhat undistinguished galaxy. There are much prettier galaxies. This one's called NGC 4414. That's a real photo. That's really beautiful, isn't it? So those people have to pay more because they've got a view. I want to stress this idea of size just a little bit. That's an undistinguished piece of sky. The little L-shaped thing in the middle is about 1/1,000,000th of the sky, chosen not at random, but because there are very few foreground stars in it. It's like looking out of the plane of our galaxy, out into deep space, wondering what you see. The Hubble Space Telescope spent not a whole lot of time, but I think a week or two, taking the best picture it could of that little L-shaped piece. And there it is. It's called the Hubble Deep Field. If you look hard enough, if you wait long enough to accumulate enough light, there's a lot of stuff out there. That tiny little region of space, 1/1,000,000th of the sky, has all of these galaxies in it. And even the things that are little tiny dots, when looked at very closely, are with one exception. There's one star on this image. And I don't see it. There it is. All the others are galaxies. Looking even closer, there are lots of different kinds of galaxies. Some of them are, edge on. Some of them are edge on. Some of them are side on, so we get a good view of them. Some of them are blobs. They come in many different kinds. I mean, these are the supermodels of galaxies up here, but they come in things ranging from blobs to spirals and barred spirals. We are a barred spiral. We're one of these kinds. And there are a lot of them. Now, you might want to know a little bit more about ours. Let me come back to this one. This is an actual picture from the Earth toward the center of our galaxy. This actually isn't toward the center of our galaxy, but it's a better picture. Most of what you're seeing there that's white, this idea that the Milky Way is just lots and lots of stars. The black looks like a hole. It looks like, there's a gap. But what that really is dust. That's soot, black dust, that's preventing us from seeing those regions. And in fact, there's an unfortunate amount of black, sooty smoke between us and the center of the galaxy, just the part you'd want to see. As you learn about an invisible light, however, it's not just visible light that can help. Once astronomers started to work with other kinds of light, this is a picture of the Andromeda galaxy, our nearest neighbor galaxy. Up there, you can see these dark bands. Imagine if you're here looking through those bands, it'd be hard to see. When you look at them in infrared light, which has been falsely colored, you couldn't see it if it was really infrared, but where it's bright infrared, we make it bright in yellow. This is dust. All those dark bands are dust. And by choosing the right wavelengths of infrared light, you can see through that dust. This is an image of the center of our galaxy. So, how many of you know there's a giant black hole at the center of our galaxy? A few of you. There's a giant black hole at the center of our galaxy. Does this alarm you any? No, you've got finals in 2 weeks. You don't have time to be alarmed. The scale of this is almost, but not exactly, if that was the sun, this would be our nearest star. Actually, it would be right about there. So this region right here is just full of stars. Not full of to the extent that they're as close together as the Earth and Moon. Not full of to the extent that they're as close together as even the sun and the Earth. But full of to the extent that, remember that Oort cloud? That wouldn't, if we were in this region, that wouldn't be full of comets. That would be full of stars. This is a very dense region of stars at the center of our galaxy. And at the center of that, we now believe there's a black hole. Well, why do we believe that? Now I got to figure out how to make this go. Did that move? How do I make this go? Hello, cursor. Well, I'm going to do that this way. See them move? They're sort of hitching back and forth. They're not moving continuously. I'm sorry that video is not working, but that's 11 years of infrared observations of stars moving. This is not an animation. These are pictures taken with a telescope of stars moving around in the center of the galaxy. This is a slightly larger view. These are stars that are a little bit farther out. Let's see if I can get that one to go. Is it moving? Yeah, that's not going to work. Okay. Now I got to figure out how to get that back over here. There we go. And we'll play that. So science is really about data, not about pictures, at least as far as physicists are concerned. It's still not working. So here is an observed orbit of a star. 1994, 95, 2001, 2002, 2002. It's going around like that. We actually there is more data. This is done by some people from Berkeley and some people from Munich. This here, this little, is a radio bright part of the galaxy, a place where we see a lot of radio emissions. It's not quite in the right place to be the gravity that's causing this orbit, which should be right about there. So, we don't have any way of knowing whether it just happens to accidentally line up or something associated with is the source, but there's nothing visible there. Whatever it is that these stars are orbiting around is invisible. This is not an animation. It's just a nice way of showing it. This is real data. All of those, this is not a simulation or anything like that. All of these dots are real places where stars have been seen. Then we extrapolate it out. Here's one that's going around. We extrapolate it that way. Here's this one that I just described. This is one whose orbit is a little bit tilted with respect to us. All of them come together to locate what seems to be the central mass of our galaxy right there, right next door to this little tiny radio source, the red dot. From those orbits, you can calculate how much mass there is inside them. The bigger the mass of something, the faster you orbit around it because the more gravitational pull you've got. You can calculate, what this plot is saying is that for things that are orbiting farther and farther out, they're actually orbiting around lots of stars. They're being pulled in by this whole cloud. But once you get in very close, you find out that there's something that's got about 2.5 million times the mass of the sun in a very small region. It's such a small region. Watch this here. See that little, right there? See that little tiny flare? I'll let it run. The infrared astronomers were watching this little region, and they discovered that something flared up from being not really very visible to several hundred times the brightness of the sun and back down again in 39 seconds. Now, let's think about this for just a second. This is something that got really, really bright over 39 seconds. How big could it be? If it was huge, like so big that it takes light a minute to get across it, well, how would it know to all turn on at exactly the same time? When something lights up and then goes dim again over 39 seconds, it can't really be much bigger than 10 light seconds across. Maybe 20, maybe 5, but it's got to be something of that scale. Whatever it is that's glowing like this is a tenth the size of our sun. It's much smaller than our sun, much brighter than our sun, and it's sitting right next door to where we predict this black hole will be. So black holes are very interesting to people, and we could talk about the physics of them, but this sort of seems to meet the definition. It's a very massive, we don't know how to make stars that are 1 million times as massive as our own, object that you can't see. Black holes are supposed to be invisible, right? How many of you think you can see black holes? What would be the point in calling them black if you could see them? It turns out that much smaller black holes you actually can see. The first one that became a candidate for it is called Cygnus X1. This is this solar system picture that I've got. All these little dots are now, I can tell you that these are all galaxies. But also buried in that picture is this. Another piece of serendipity. An X-ray detector was mounted on a telescope, and it was mounted on a rocket and was sent above our atmosphere. Our atmosphere shields us from X-rays, to just sort of look and see what the sky looked like in X-ray wavelengths. And they found, mostly it's sort of undistinguished, but there's one incredibly bright spot in that constellation. You study it in more detail, you measure its spectra, and you discover that this is iron. This is the X-ray spectrum of a piece of iron. So it's somehow iron emitting X-rays, but this is very redshifted. What that Cygnus X1 probably is a star being torn apart by a black hole. It's probably, there's the black hole with extremely high gravity. This is another star that's being torn apart, and as its stuff gets sucked in here, it forms what's called an accretion disk. It can't fall straight in because it has a little bit of rotation, a little bit of angular momentum. Just like the Earth doesn't fall into the sun because it has some rotation. So as the stuff comes in, it starts to swirl around. But it's a gas, and it gets friction. It runs into the other atoms, starts to lose its energy, gets hotter and hotter from all these collisions as it's getting pulled in closer and closer, gets more and more gravitational energy from being pulled in, gets hotter and hotter, gets heated up, not white hot, not red hot, not white hot, not ultraviolet hot, but X-ray hot, millions of degrees, and that's what we see coming from there. It's not the black hole that's bright. It's all of the energy of all the stuff that's falling into it that's bright. There's so much gravity in a black hole that the amount of energy you get from dropping something into it is comparable to the mc squared rest mass relativistic energy of it. It's a very efficient way of making something into energy. The one in the center of our galaxy has just cleaned out all the junk. Every now and then something big falls in and we get a flash, but all of the gas in the vicinity has been cleaned out over the length of time that it's been there, so it's not active. Galaxies viewed a long time ago, if they're far away, we're seeing them a long time ago, often do have central black holes that are very, very bright and disruptive. This is one where here's an ice galaxy. This is overexposed, but if you look at X-ray wavelengths at the center, the X-rays from the center of that galaxy are extremely bright, sterilizingly bright. To go back to the Drake equation, there's nobody living here because that central source in that galaxy is still extremely active. I'm 3 minutes behind, and I got to figure out why. Okay, back to us. That's our galaxy again. There's Andromeda. If you really want to understand galaxies as a scientist, you start to become very, very quantitative. You look at lots of details. One of the things you can look at in a galaxy like this is how fast are those stars moving. It's very hard to measure this. They don't move very fast this way. It takes many years to go around. But they're moving fast enough in miles per hour that you can see whether they're coming toward you and whether they're going away from you. Using the Doppler shift of their light, for the ones that are out here that are probably either coming or going, you can measure subtle differences in their colors in their spectra and see which way they're moving. And the obvious first question is it really swirling or is it unwinding? Which way does it turn? And they turn in the swirling direction. But when people started to do that and started to make plots of both from the stars, or from the gas and dust, they made an interesting discovery. They discovered that the stuff doesn't behave the way you expect. Because in our solar system, most of the mass is in the sun. And because of that, as planets are farther and farther away, they're less attracted by the sun, and they move slower. In a galaxy, the situation is a little bit different. As you get farther and farther away, there's more stars inside your orbit. So the mass that you're feeling attracting you back to the center grows a little bit. So as you go farther and farther, as you start at the center and grow out, you expect that the orbits will be faster and faster until you reach some sort of peak, which is where the central bulge is. And as you go farther and farther out, now you're getting farther away, and you're only picking up a little bit more extra material because the galaxy is basically a bulge with some decoration on it, and you expect that it will drop off like that. So you expect the speed of stars in their orbits to go up really quickly and then slowly drop off. And right around here somewhere is where you would say, there's nothing more. There are just a few more stars. That's sort of the edge. Most, but not all, galaxies don't work like that. Most, including our own, look like this. Well, what's that say? That says that there must be some extra stuff that we're not taking into account. Our prediction that this will drop off is based on the fact that most of the matter is munged in the center. And if it was more spread out than that, if there was something we can't see, well, that would cause more gravity and make these things more fast. So you have to be very careful. You have to start paying attention to things like not just the stars that you can see, but also the dust that you can see in infrared. And you have to look not just for dust, but for gas, which you can observe several other ways. You even look for sort of swoopy, ugly stuff. This is not a photograph. This is a computer reconstruction. This is our galaxy. That's us. This is a swoopy thing of stars that completely surrounds us that seems to have been a galaxy that we collided with or collided with us. It's a no-fault insurance state. We're not sure who did it. That was disrupted, was destroyed, and all these guys were just sort of thrown out. You can look for that kind of stuff too, but in the end, you can't explain it. In the end, you keep finding galaxies that look like this, where you can, this is a very old galaxy. There's very little dust in it anymore. It's all been swept up. This is what we predict from the light for how fast things go, and this is what we measure. Not we, I didn't do this, but what people measure. And the only explanation we've got is none of the above. We give it a name because physicists are really good at giving things names. We call it dark matter. It's matter because it has some sort of gravitational attraction. It's pulling things in, and that's what matter does gravitationally. It's dark because we can't see it. It's not like dark like erasers. It's not velvet. It's dark, doesn't have any electromagnetic reaction. Light does not interact with this. People are pretty convinced that if it was atoms or molecules or even protons and electrons or anything else like that, any kind of the stuff that we're used to, we'd see it. But we don't. Some galaxies have a lot of it. Some galaxies have a little. Ours is pretty much typical. When you sum up the amount of dark matter and the amount of regular matter in the universe, there's more of this stuff. We're still working out exactly how much, but there's 3 or 4 times as much of this stuff as there is of us stuff. That's really cool. Because I'll show you all we know about it experimentally in the laboratory, not from indirect observations, but from direct observations. Nothing. It's really dark. We don't know anything about what makes this stuff up. Have a lot of theories, have a lot of experiments to do. We don't know anything about it. We even know a little bit about it on a large scale, this is one of my favorite astrophysics pictures. What you're actually looking at here, that's a pair of galaxies that have collided. One was coming in this way and one was coming in that way. And this part, this colored image in the middle, is sort of the debris from that collision. So what's these two lobes? Those two lobes are X-ray bright regions of hot gas. Now, if you've got something that's really hot, it's moving really fast. So if you have something that's been there for a very long time, this collision took place a long time ago, that hot gas would have had enough time to completely escape, to just use the motion from its thermal energy to just fly away out of this picture, unless something was keeping it, unless something was causing those hot gas molecules to orbit and to stay in one place. They're orbiting this. This actually tells us something about what makes up dark matter. You have a galaxy full of people stuff, dust, stars, a galaxy, and surrounded by dark matter, another one surrounded by dark matter, and you collide them. And all the dust runs into each other and stops. The cars crush and stop. But the dark matter just goes whipping on through. It didn't hit anything. So these are the stopped galaxies. Here's the cloud of dark matter that was originally going this way. Here's the smaller one that was originally going that way. And it's still gravitating. It's still attracting stuff because it has gravity, and it's sort of picked up all of this hot gas from around it. It's carrying it with it. Come back in 1 billion years, and this gas cloud will be over here somewhere with no galaxy in it anymore. It'll be a dark matter galaxy of a little bit of gas and a lot of dark matter. Way cool. Okay. What's that a slide of? That's a slide of what we knew about where the universe came from and was going to as of 150 years ago. Nothing. If you look at the night sky, you see a few planets that are moving around. You see some spots on the sun, if you know how to look. They change a little bit. You see lots of stuff that's near the Earth, clouds and stuff like that. But the stars don't move. Over a human lifetime, you can't see the stars move. Even with the best instruments that we could make 1,000 or 500 years ago, the stars don't move. They move a little bit, and when we had telescopes 200 years ago, there were a few stars that you could imagine beginning to move. And when we had photography, we got better at keeping records to see tiny little movements. But basically, the heavens don't move. So for a long time, the official view of the universe was that it had been always sort of like this. Let's discuss the details. Maybe it was infinite, maybe it was not. But, you know, nothing much changes. We couldn't imagine a beginning. And then, in 1929, that guy made that plot. Now, this is Edwin Hubble. I got to tell you a story about Edwin Hubble. He went on to have the Hubble Space Telescope named. You've heard of the Hubble Space Telescope? It's named after him, so this must be important. What he measured was a plot of how far away galaxies are, pretty much based on how bright they are. If you assume that they're all about the same brightness, the ones that appear dimmer to you are farther away. So if you assume they're all sort of the same, the ones that appear dimmer are farther away. And then he plotted that against how fast they were moving. And if the universe was constant, you wouldn't expect anything different, right? Galaxies that are far away and galaxies that are nearby, everywhere in the universe is supposed to be the same. Let's see what the plot looks like. Some large fraction of science is just making a plot that you expect to have nothing in it and being prepared to be surprised. This is the expanding universe. The idea is that not only when you look at something that's this far away, you're also looking at something that is back in time, because it took time for that light to come to you. Ignoring that for just a second, what he found, and was later found to be true, was that no matter where you look, the universe is running away from you. And the farther away something is, the faster it's going away from you. I remember discovering this when I was in high school. And I said, God, everybody hates me. All the galaxies are running away. The reason high school comes into this is that the high school I went to, when I left New York and I moved halfway through my freshman year, I moved to Illinois, tiny little town, really tiny town. The only three things it had going for it was that it had three famous people who had gone to the high school. One of them didn't graduate. John Belushi. You know who John Belushi is? Dead comedian, Animal House, Blues Brothers, etc. Red Grange, who you've never heard of, but was a famous football player in the 1912s. And Jim Belushi, who actually was the only one of the three who had graduated from the high school. And Edwin Hubble. So the science teacher was really cool about the fact that Hubble had gone to this high school. 11 years ago, they had to change this high school to a middle school because of demographics changes. And all the old people in town wanted to name it Red Grange Middle School. And all the young people wanted to name it John Belushi Middle School. But they couldn't do either of those because nobody had heard of Red Grange, and they can't name it after a dead comedian. So they decided they were going to name it after Hubble, famous astronomer who discovered that the universe is not static, that it had a beginning. And the town voted 75% to 14% not to. Because, quote, he wasn't a regular guy and he never played football in high school, end quote. No, now it's just called Wheaton Central Middle School. So, you know, even a prophet in his own time is not well appreciated. What does it mean that the universe is expanding? Well, there are two things that it doesn't mean. It doesn't mean that you're in the center. There's nothing magic about us. Anybody else who made that same plot, like this galaxy over here, would discover the same thing. He would discover, or she would discover, that this one's going away, just not as fast, and that we're going away, just not as fast. Another way to see that ignore the fact that this is a sphere. This is just a nice, convenient way to have a piece of rubber. If I put a bunch of dots on this, and blow it up some more, the dots get further apart, right? And because the rubber is stretching everywhere the same, is any one of them special? Every one of them is seeing its neighbor dots get farther apart. Every one of them is seeing its neighbor dots go away, but none of them's special. They're all seeing that. They're also seeing neighbor dots that are farther away go away faster. Okay, we're going to shrink it a little bit. If I double this distance in a second and double that distance in a second, they're both doubling, but this one's moving much faster. Every billion years, this guy gets twice as far away, and this guy gets twice as far away. This one's moving much faster. So the ones that are farther away sort of naturally move faster if what you're seeing is the space between the galaxies is getting bigger. There was an immediate reaction from the astronomical community to this. There were a lot of challenges of the method, and here's a cartoon of the method in its more modern form, not the way that he did it, but you take a very standard object like a supernova, you measure how much its color has shifted, and you measure how bright it is, and you make a point on one of these plots. There was an immediate reaction because it was obvious that if you ran this record backwards, if you thought about what was happening not in the future but in the past, everything was coming closer and closer together. And at some point in the past, a time which you can calculate from the slope of that plot, the universe did not have separate galaxies. It was all smunched together. We were not separated from the Andromeda Galaxy because everything was in the same place. How old is that? Well, here's a plot of sort of how science works. The right plot up here is this value, the Hubble constant, which you can convert into the age of the universe based on his first paper, measured over time. And as time goes on, now there are a lot of measurements being made. It's becoming a more and more accurate number. It turns out to be smaller. The universe turns out to be older. The expansion is slower than it was originally thought. Hubble did make a few mistakes in his original data because he really didn't have a good yardstick for how far away things were. It's hard to know how far away things are in the sky. But the expansion is still very, very true, and the age of the universe is somewhere around 15 billion years. It raises the obvious question of what happened at the beginning. So if this is now, and a while back things were closer together, at some point they must have been close enough together that it doesn't really make sense to think about galaxies. And if you go back even further, you reach a point where it doesn't even really make sense to talk about people. And if you go back even further, you reach a point where it doesn't even make sense to talk about atoms, because everything was so dense. There was so much energy in one place, everything was so hot. If you go back even further, it doesn't even really make sense to talk about protons. And behind that, it just really doesn't make any sense. As a laboratory for understanding our theories of fundamental physics, what they predict for what happens here is one of the hardest tests for those theories to pass. If you make a theory of what the fundamental physics of the world is, not atoms, not protons, but below that, it better pass this test. It better predict that as you start with a very high amount of energy that cools down and expands, that we get something like protons and hydrogen atoms and stuff like that. Now, one of the things that's left over from this, first off, what is this called? What's that? The Big Bang. Okay, you all know it as the Big Bang. They even named TV shows after it. The Big Bang was originally coined to make fun of this theory. How could you imagine a theory that predicts, how can you imagine Hubble's observations are right if it predicts that the universe must have started in an explosion? Well, you know, sometimes, even though it's an idea that we make fun of, it turns out to be right. And the real clincher in this came in 1964, I think, when Penzias and Wilson saw not this stuff, but the stuff that's in between. As the universe expanded and cooled, it went from being so hot that there wasn't such things as protons to so hot that there were protons, but there weren't such things as atoms. The sun, for example, all of its hydrogen's been ripped apart into individual protons and electrons. And because of that, those are charged particles that interact very strongly with light. That's why you can't see through the sun. Any light will bounce off an electron or a proton in it, scatter and be bright and all that stuff. Gases like air, where the electrons and the protons are associated in atoms, are transparent. So as the universe cooled, there came a point where it was cool enough that all of a sudden hydrogen could condense. All of a sudden, protons and electrons could get together, get married, settle down, and have kids. And light all of a sudden became transparent. That gas was not like the plasma of the sun, but light could travel through it. And that light started traveling. Some of it has traveled for 14 billion years, managing to miss everything, and then the Earth gets in the way and it hits the Earth. This is called the cosmic background because it comes not from stars, but from the very beginning of time. It's been traveling forever until it finally hits you. Radiation, because it's radiation, sometimes called the cosmic microwave background radiation. It started off as light, like the sun, but over time, as the universe has spread out, its wavelength has gotten longer and longer, and now it's microwaves, sort of television frequencies. Penzias and Wilson discovered it because they were trying to find interference in a transatlantic radio link. And they basically ruled out everything. They ruled out electronic problems. They ruled out pigeon droppings. They ruled out all sorts of stuff. And what was left was it comes from the sky. They checked that. They said, oh, my God, it comes from the sky. It's what's left over. People started to study it. This was an experiment that was flown in a U-2 spacecraft, U-2 spy plane, to compare the microwave background radiation from this direction with that direction, because the Earth is probably not standing still with respect to the early universe. So if we're going toward this stuff, it'll be shifted to be blue and hotter. If we're going away from it, it'll be shifted to be red and colder. that U-2 spy plane only managed to look at a few tiny patches of the sky, but in fact they found this shift, and they worked out that the Earth was moving about 300 kilometers a second, which is really very fast. Not 300 kilometers an hour, 300 kilometers a second. This is the paper. I noticed the authors. You've never heard of him. He's got a Nobel Prize, and this is someone you know. This is a better picture of it. This is you're looking at sort of the sky. The middle of that is that, remember that Milky Way slice that I gave you? That would be this. This is the hot part, the direction that we're going toward. This is the cold part, the direction we're going away from. The coding is a little bit backwards from Doppler shifting. That's the original image. This is a more, well, we'll come back to that one in a second. Our view now of the way the universe was created and expanded is a little bit more complicated. This is a nice cartoon. Time goes this way, about 14 billion years. Something that we really don't understand caused the beginning of this, and there was a huge, very rapid expansion. The easiest way to think about this is imagine that you've got liquid water in a pot at 212 degrees, and it's just about to boil. And every now and then, one little spot of it decides to boil. And you get a giant bubble that just goes whoop, and rises to the surface. Our current theories is that we're a bubble. There was a whole bunch of energy available for this little bit of space to, quote unquote, boil, and all of a sudden it decided to expand. And over the course of a very small amount of time, probably less than a second, it grew to be quite big. Ever since then, each of these bands is about a factor of 10. We've been slowly expanding. The universe has been getting more complicated. There was this period of growth here resulted in hydrogen gas. There was a long dark period until there was enough time for that hydrogen to fall in and create the first stars. It takes a long time for gas to fall in and get dense enough and the star to ignite. So that's called the dark age. The first stars came along after about 400 million years. They were really, really big, and they were burning just pure hydrogen, so they lived very short periods of time. But in the process of blowing up, they created all these guys. Here were created from primordial hydrogen and a little tiny bit of helium in those first stars. And then we get galaxies and planets and physics 10 and all this other stuff. And that's a satellite that they built to look at this. If you really want to understand that expansion, the best way to do it is to pick something that's 4 or 5 or 10 billion light years away and study it. If you look at something that's 10 billion light years away or 5 billion light years away, you're also looking that far into the past. You're looking at because that's how long it took the light to get here. So if I'm looking at a galaxy that's 5 billion light years away, I can't see what it's like today. Just like I can't see what's happening on the sun right now. You can't get a Twitter from your friends in New York about what they're doing right now. You find out what they were doing 5 milliseconds ago. Okay, 5 milliseconds is not a big deal, but 5 billion years is. So if you look far enough out at something that's very, very small, you're looking at what was happening a long time ago. We can do this Hubble thing. We can look at galaxies that are very far away and measure how fast they're moving. But in order to get a very accurate measurement of how far away they are, we need something standard. We need what's called a standard candle. We're going to say the dimmer it is, the farther away it is, but I need to know how bright that is. If I'm looking at a 100-watt light bulb and a 1,000-watt floodlight, and I see something of a certain brightness, well, this guy's going to be farther away. I need to know something. What's being done these days is you look for a particular kind of supernova, a star that explodes because gas is being added to it by a neighbor. And when it reaches a certain size, it explodes. And they're all pretty much the same size explosion. So one way to do it would be to sit here and look at that galaxy for like a million years, hoping that it would get a supernova. Well, you don't actually need to wait that long. For many galaxies, 10 to 100,000 years would be sufficient. You could have one graduate student look at a galaxy and another graduate student look at another galaxy, but this is just not the way to go. What's done is you take a picture of a lot of galaxies, and then you wait a couple weeks, and you take another picture of that same cloud, and you look for small, tiny little differences in between them. A star that has greatly brightened during that 3 weeks. That's a supernova. And then you bring on a huge space telescope and take a look at them and understand them in great detail. There's the Hubble Space Telescope. There's the galaxy. There's the star. The little telescope that you can get time to do this with can't resolve it, can't see it as clearly. But that's okay. You can still discover the supernova. And you can make a lot of these. When you do that, here again is that picture. What you're really trying to do is to test this Hubble diagram, this connection between redshift and distance. It's actually a somewhat complicated thing. It involves a lot of data processing and signaling back and forth between continents and space telescopes and all this crap. But when you get that done, you make a very interesting discovery. Our basic theories of gravity, without going into too much detail about why, would predict that this expansion is slowing down. The original bubble that formed had some kinetic energy, had some momentum, had some flying away. But there's a lot of mass there. There's a lot of gravitational attraction there. All these things are pulling on each other, and they should slow each other down. And so you expect that they will slow down a little bit over time. If there's a lot of mass and not a whole lot of head start, maybe it'll slow down, stop, and fall back into a big crunch. Maybe that's what was before the Big Bang. There was a big crunch, and then it exploded back out again, and we're doomed to repeat this every Tuesday. On the other hand, maybe there's enough energy that the stuff will expand forever. There's not enough gravity to stop it. And in between those two is the place where there's just enough to stop it, to bring it asymptotically to a stop. Between too much and too little, there's a just right, the Goldilocks case. Experimental question. You'd like to know. One way you can do this is to make this redshift plot and then look to see if it's curved, because the farther back, the farther away you are, the more light years away something is, the farther back you are. You can check to see if this expansion is changing over time. It was only with modern computational work in the last 10 years that it was possible to look at enough galaxies to be able to do this, because you've got to look at a lot of galaxies if they only blow up every 100,000 years or so. And guess what was discovered? Well, some people thought that clearly the universe was going to fall back into a big crunch, because that explains where it came from. Some people thought it clearly didn't have enough energy, because you can do some calculations that would sort of point you that way. There's a certain amount of people who believe, the universe has to be just right because that's the definition of just right. The answer is none of the above. Nature does this to us. If we're too smug in our list of possibilities, she likes to choose none of the above. The acceleration of the universe is expanding. Something in the universe is repelling all of the galaxies that make it up. We have very good evidence for the Big Bang. That microwave background radiation there is excellent evidence for the Big Bang. It tells us a lot about what happened, and even tiny little fluctuations in that Big Bang form the little seeds around which gas condenses to make galaxies. And so we can connect the Big Bang detailed, why am I pointing with that? The Big Bang detailed properties with how galaxies eventually condensed. And all of that makes perfect sense. But the most recent supernova observations indicate that instead of time is now starting at the bottom, instead of now this bubble expanding to cause really hot plasma that eventually did this dark region with some of the very earliest stars and then galaxies and then now, and it pulling back together, or maybe even just going out, becoming straight, it's expanding. Something is repelling the galaxies, and it's something that repels more as time goes on. Well, matter attracts, so dark matter's already been used. We don't know what this is, so it's dark. Dark in the sense that we don't know anything about it, opaque. So we call it dark energy. We actually know a little bit about it, more than I can go into right now. But this, less than 10 years old, is where we are now. We're trying to understand this dark energy. Whatever it is, it's 70% of the universe. We know how much it is. It's 70% of the universe, and that's all we know about it besides that. Thank you all very much. It's been a pleasure being here. This is my last lecture for the time. Good luck on your final.